A K2 and A K1. So this is second quantized Hamiltonian, assuming that the U of Q is a Fourier transform of your realistic potential, which describes how particles interact with each other. On the last lecture, I wrote the same Hamiltonian, assuming first of all that UQ is a constant, because in real space it's a delta function. Fourier transform of the delta function is constant. And then I wrote this Hamiltonian in the coordinate time representation. Now I don't consider any dynamics. So there is no time in this problem. I'm not discussing propagating of the fluctuations or collapse of the condensate. I will be interested in diagonalization of this Hamiltonian. This is a goal for whole my lecture today. However, you should digest that this is Hamiltonian written in the language of second quantization. Operator A are bosonic operator subject to bosonic computational relations. It's a Schrödinger picture. The operators do not depend on time. Therefore, the commutation relation, I don't need to take care at which time moments they are defined. So I will proceed with this Hamiltonian. In the same language, M is sum over K, A dagger A, K. So I omit putting heads, but A are operators. And we consider the situation when we are below temperature of Bose-Einstein condensation, Bose-Einstein condensation. So I would say much below, and for almost all calculations which I'm going to consider today, I will just use zero temperature limit. So we are in the ground state. So we discussed that if we are below Bose-Einstein condensation temperature, we need to take this sum in a special way. Namely, Bose-Einstein condensation assumes that there is a macroscopic number of particles of the order of 10 to the power 23, which occupy state with a zero momentum. Therefore, I need to write A dagger node, A node, which means K equal to 0, plus sum over K not equal to 0, A dagger K, A K. Okay? So, this is a Hamiltonian. The expectation value of the Hamiltonian gives me energy. This is an operator of number of particles. The expectation value of this operator divided by volume gives me density of the particles. Okay, what I see from here, this is a node, and a node is macroscopically large parameter. I would therefore assume that creation and annihilation operator, you remember, operator A dagger acting on a state n with n particles transfers to the state n plus 1. Operator A acting on a state with n transfers to the state n minus 1. So these matrix elements are different from 0. However, since a node is macroscopically large number, I will replace operator A dagger node and A node by square root over n node. So I would say that instead of A node, I will write square root over n node. And the same for A dagger node. So it's a classical variable. It's a huge number. Square root over n node. Therefore, this is the way I'm going to treat the Hamiltonian. Let's look at this term. This is a kinetic energy. This is interaction. Let me visualize this interaction using some cartoon, which actually has a deep sense. So what I have here, there is state with K1, which is annihilated. There is a state with a K2, which is also annihilated. Annihilated means the arrow comes to the right direction. And then these particles interact and they transfer momentum q. So as particle with momentum k1 interacts and momentum is conserved, here we have k1 minus q, and k2 picks up the momentum, and we get k2 plus q. So what do we see on this graph? So this wavy line corresponds to the interaction uq. And here we have two annihilation operators with a momentum k2 and k1, and two creation operator k1 minus q and k2 plus q. So this diagram is known as a Cayman diagram. This is a very powerful language of computation. I'm not saying what the straight line means, because straight lines actually are related to certain green functions. This is a technique used in quantum field theory, in high energy, in condensed matter. We are not going to dwell into this business. I plotted you this cartoon in order to visualize this term, and now we are going to consider the situation when some of these operators are in the Bose-condensed state. Namely, we will have 4 ends. We will put either all 4 ends, all momentums equal to 0, or any 2 of them. There are several combinations. And therefore, assuming that n node is very large, we will keep term in the Hamiltonian, namely in the potential energy, which is proportional to n node square and n node. And we will disregard all terms which do not connect n node. It will be great simplification. Our Hamiltonian, which contains 4 fermion creation and annihilation operator, will be reduced to the Hamiltonian, which contains only product of creation and annihilation operator. Therefore, we reduce our problem to quadratic form. But the quadratic form which we will obtain is not yet diagonal. So we will apply additional tool method known as Bogoliubov transformation in order to transform this Hamiltonian into the diagonal form. As soon as we do it, we succeed. So this is the logic. Okay? And please consider this cartoon just as a visualization of the process. Okay, good. Good. So, first of all, let's consider the situation where all momentum, I will call this situation 1, where K1 is equal to K2 equal to Q is equal to 0. So then H interaction 1, so 1 corresponds to this, is equal to. So this is H interaction. So if all momentums are equal to 0, I will replace each of the operators A node by N node. So square root of N node, so I have 1/2 U at the momentum Q equal to 0 divided by B times N node square. Right? I have a product of 4 square roots of a node, so this is a constant. And once I wrote Q equal to 0, in all the rest calculations, I will write U with the argument 0. Argument 0 means the momentum equal to 0. And I spent some minutes last time in order to show you that this U at the momentum equal to 0 is a constant, so well-defined quantity. If I'm dealing with the Coulomb interaction, which diverges as 1 over Q squared, I need to say a few words how we consider Q equal to 0. But so far, U at 0 momentum transfer is very well defined quantity for neutral Bose-Einstein gas with a weak short-range interaction. So, number 2. Let me consider K1 equal to K2 equal to 0. So, namely, these two, K2 and K1. I replace both of them by square root of a node. So, in total, I have H interaction 2 is equal to 1/2 sum over Q, U, Q over V. V is a volume times N node times A dagger minus Q, A dagger Q. Because K1 and K2 are equal to 0. Clearly, if I put 3 momentum equal to 0, I will automatically get fourth momentum equal to 0. This comes from the conservation. So this diagram, by the way, respects conservation of the momentum in each point and conservation of energy. So, number 3, I can consider K1 minus Q equal to 0 and K2 plus Q equal to 0. Namely, I will consider these two arguments equal to 0. It means that K1 is equal to Q and K2 is equal to minus Q. I have H interaction 3 equal to 1/2 sum over Q, U, Q divided by V, and node A minus Q, A, Q. So, you see that I already collected the leading term, which is a constant, which is proportional to the square of the large number, and first two terms, which are linear in M node. So let me now consider situation number 4. In situation number 4, I will take one argument like this and that equal to 0, and two remaining are not equal to 0. So therefore, in general, I will get terms A dagger A, which are already diagonal. And there are 4 possibilities to do that. Situation A, K1 minus Q is equal to 0, K2 is equal to 0. So H interaction for A is equal to 1/2 sum. K1 minus Q is equal to 0, which means K1 is equal to Q. K2 is equal to 0, so we have A dagger Q, AQ. So this is sum U, Q over V, and node A dagger Q, AQ. So B, if I consider K1 equal to 0 and K2 plus Q equal to 0. So this is K1 equal to 0, K2 plus Q. You see, from the point of view of diagrams, I have either diagrams, say, like that, and typically I need 2 color chalks. These are condensate lines, square root over n node, square root over n node. This is a case 2, well, this is a case 3, or I have a diagram. This is a case 2, or I have all sorts of diagrams. This is a case 4. So the diagrammatic language is very powerful because you can visualize what you are doing, and it's also powerful from the point of view of doing calculations. So H interaction for B is also equal to 1/2 sum over Q, U, Q, B, and node A dagger Q, A, Q. So now I have 2 more possibilities. I will write it here. So possibility C and D for C. If I take K1 equal to 0 and Q equal to 0. So K1 equal to 0 and Q equal to 0, which means K1 minus Q also equal to 0. We have only these two terms. So H interaction for C is equal to, now we have U at Q equal to 0. So this is 1/2 U node over V times N node, sum over K, A dagger K, A K. And the last possibility, D, is when K2 is equal to 0 and Q is equal to 0. K2 is equal to 0, Q is equal to 0. This term go to the condensate, and we have H interaction for D, which is also equal to 1/2 U node over V times a node, sum over K, A dagger K, A K. Good. So the last thing which I would like to do is, let's look at this term. I will call it E node. This is a constant, which is 1/2 U node over V times N node squared. But I would like to deal with the total number of particles. Therefore, using this line, I will rewrite it as 1/2 U node over V times N squared. But N squared is N node squared is N minus sum over K, A dagger K, A K squared. And therefore, it is equal to 1/2 U node over V times N squared. I open the bracket. Then I consider the term which is a product N times A dagger K, A K. This is K not equal to 0. Actually, everywhere in these sums, I assume that summation is over momentum not equal to 0. So this is minus 1/2 U node of V times N times 2 sum of K, A dagger K, A K. And everywhere else, in all terms 2, 3, 4, I'm going to replace a node by N, because difference between a node and N is of the higher order than I consider in my calculations. So therefore, sorry?
I'm not able to see 4C.
4C. This is 1/2 U node divided by D and node sum over K, A dagger K, A K. The same as 4D. 4C and 4D are the same. Okay?
Thank you.
So, with this trick, I replaced everywhere N node by N, the total number of particles. Now I'm collecting everything what I have written before. And writing down my new Hamiltonian. So this Hamiltonian is exact. Let me write down H tilde as approximate Hamiltonian, which actually obtained from my initial exact Hamiltonian by dropping off terms which do not contain N, large number. So this is approximation, and this is simplification. So H tilde is equal to E node tilde. So I will call this constant term as E node tilde plus sum over k not equal to 0. I have epsilon k plus actually two terms times 1/2 times u k over v times a dagger k a k. These two terms is for a plus for b, right? Then I have term, two terms times 1/2 u node over v sum over k a diagonal k a k. This is for c plus for d. Then I have this term out of E node minus 2 times 1/2 u node over v sum over k a dagger k a k. This is from E node. And you see that these two terms exactly cancel each other. And what remains are two terms plus 1/2 sum over q, u q over v, and I have terms a dagger u, a dagger minus q, plus a minus q, a q. Okay, so as you see with this trick, actually, we get rid out of potential considered at zero momentum. So from now on, my calculations are general enough to be applicable for the long-range potential as well. Good. So we have a new Hamiltonian, as I said, which contains part which is only diagonal and part which are not diagonal in terms of creation and annihilation operator. We need to transform this Hamiltonian to new Hamiltonian. H tilde is equal to sum over k, e k, b dagger k, bk. Because if we succeed there, we are saying that we found the new excitations, which are going to be bosons B, and the energy of these excitations is E capital K. So this is our goal. This procedure is known as the diagonalization of the Hamiltonian. The new operator described as new excitations. Okay, so let's go. And mathematically, we are going to take a quadratic form and bring it to the diagonal form. The meaning of this diagonalization is that we reduce our system to non-interacting modes, like non-interacting harmonic oscillators, which you consider in classical mechanics. So we started from the system of interacting modes, and at the end of the day, we are going to define new modes which are not going to interact. Actually, most of things done in many body physics are related to diagonalization of the Hamiltonian. It can be done either analytically, in the case I demonstrated, or numerically with exact diagonalization technique. But to say truth, in most of our time, we are dealing with diagonalization of the Hamiltonian. Okay, in order to proceed with the long but straightforward calculations, I would like to introduce usable notations. So I will define sine k as epsilon k plus what plus, give me a second. I will define beta k as 1/2 UK over beam times n. Sorry, there should be n somewhere. Of course, why didn't you tell me? So there is n here, there is n here, and there is of course n here. So I will define this quantity 1/2 u over v times n as a beta k, and psi k is epsilon k plus 2 beta k. So to say this is psi k, and this coefficient, if I write n here, this coefficient is beta k. Okay, assuming that I can write down my Hamiltonian H tilde is equal to E naught tilde plus sum over k psi k A dagger k k plus sum over k beta k A dagger k A dagger minus k plus A minus k A. So we proceed from H to H tilde. Okay? Good. Now the transformation itself. I would like to define my new operator beam, which I'm going to find through my old operator A in the form of linear superposition. Namely, I will be looking for new bosonic excitations, defining B K dagger is some coefficients UK A K dagger minus V K A minus K. So I'm going to mix creation and annihilation operator. The Hermitian conjugated BK is equal to UK. UK are some functions, so it's a complex conjugation. AK minus BK A minus K dagger. Or,
excuse me, sir.
yes.
Yes, at the point you used the index to be K and at the point to be Q. Hope they are just okay.
It doesn't matter. When I'm taking summation or integration, this is a variable of integration. I can give any name to it. K, P, Q, whatever letter you like. And this is also, well, it's enough to say that. If now I take momentum, replace momentum K by minus K, B minus K is equal to U minus K complex conjugated A minus K minus B minus K complex conjugated A K dagger. So you see that there are some unknown functions U and B. And at this moment, I would like to assume, and my assumption will then be confirmed by my calculations, that first of all, U and V are real functions. This is a conjecture. If I proceed and see no contradiction, my conjecture is correct. If I assume that U and V are real functions, and at the end of calculation, I come to contradiction, then my conjecture was wrong. So first, I assuming that UK is equal to UK dagger, and second, that VK is equal to VK star. So these functions are real. The second conjecture is that this U and V are going to be even function of K. Namely, UK is equal to U minus K, and VK is equal to V minus K. These all are conjecture. I'm going to look for solution of new variable, assuming, making conjecture that these unknown coefficients behave in this way. Okay, so I can write down that bk dagger b minus k. I'm going to write this equation and this equation in the matrix form. So this is uk minus vk minus vk uk ak dagger a minus k. So this is equation 1 and equation 3 written in the matrix form. So this is the matrix M. Okay? Good. So now the second important step. I know that my operator A satisfies both bosonic commutation relations. Namely, I'm saying that commutator over AK dagger prime, which is AK prime dagger minus AK prime dagger AK, is equal to delta K prime. So these operators commute. The commutator of two creation or two annihilation operator, A dagger, is equal to commutator AA is equal to 0. So K prime, K prime. These are bosonic commutation relations defined for the Hamiltonian, for my initial Hamiltonian. I defined the U operators. However, I would like to request that U operator possesses the very same commutational relations. I would like to deal with bosons at the end. And this requirement actually puts some constraint on the functions U and V. Okay? Because I would like to preserve commutational relations. So I request that BK dagger is equal to 1. I impose this condition. But this is what? BK is equal to UK minus VK minus K dagger. So this is BK times BK dagger UK dagger minus BK minus K minus UK dagger minus VK minus K times UK minus VK minus K dagger. So I roll this commutation relation for equal momentum, where I'm supposed to get 1 in terms of my old operators. Let's now open the brackets and collect terms. So first of all, term U square. I have AK dagger minus AK dagger AK. So there is U square and commutator AK dagger. Then there is a term VK square plus VK square. Then we will get commutator A minus K dagger A minus K. Then I have a cross terms UK VK with a sign minus UK VK. I open the brackets. So UK VK, there is a commutator AK A minus K. AK A minus K plus A minus K dagger AK dagger. A minus K dagger AK dagger. Now I see that this commutator, according to the first line, is equal to 1. This commutator, according to first line, is equal to minus 1. This commutator is equal to 0, and this commutator is equal to 0. Therefore, from the condition that BK dagger is equal to 1, having bosonic commutational relations, I immediately get that UK square minus k squared is equal to 1. If we look at this matrix M, what does it mean uk squared minus vk squared? It means the determinant of the matrix M is equal to 1. Okay? So this is UV transformation. I already got a sort of connection between the matrix elements in order to preserve commutation relations between new operators, which have to be the same as commutation relation of all operators. So this condition that determinant is equal to 1 allow me to construct inverse matrix. Because in order to express all variables from the point of view, we need inverse matrix. So the inverse matrix easily is UK, VK, VK, UK. Determinant of it is also equal to 1, of course. So what do we see here? In quantum mechanics, we, in many cases, dealing with either orthogonal transformations or unitary transformation. Orthogonal transformation is if m minus 1 is equal to m. Here, it is not the case. So this is m minus 1, this is m. The transformation is not orthogonal. Therefore, it is not rotation. We know that rotation is orthogonal transformation. We also, in many cases, deal with the unitary transformation, where n minus 1 is equal to transposed. This is also not the case for bosons. So the transformation which we found is neither unitary nor orthogonal. So what? We will see when we study superconductivity that for fermions, the equivalent transformation which we are going to use in order to diagonalize BCS Hamiltonian, Barney-Kupich-Ricci Hamiltonian, will be orthogonal. Therefore, it's rotation. And it's related to the fact that fermions subject to Pauli principle and the Fock state is compact. You have occupation numbers only 0 and 1. For bosons, we have a Fock space which is not compact. We have any occupation number from 0 to infinity, and therefore this is not rotation on a sphere, not compact. However, we can think about this transformation as a rotation on a hyperboloid. So we can write down, reparametrizing this transformation M as cos theta k minus sinh theta k minus sinh theta k cos hyperbolic theta k. So this is yet another reparametrization of my matrix, where instead of coefficients u and v, I use unique function theta k. However, the condition that determinant of m is equal to 1 is immediately satisfied because cos squared minus sinh squared is equal to 1, where cos and sinh are hyperbolic sinus and cosinus. Okay? For the rest of the lecture, I will be using notations u and v. But as a sort of homework, which I suggest you to do, I suggest to use this parameterization of m yourself alone, not now, and repeat all calculations using this parameterization. So the message is that UV transformation, which I introduce now, which in another language is called Bogolyubov transformation, for the case of bosons is neither unitary nor orthogonal. And the reason is because bosonic Fock state is not compact. Okay? Good. So now let's proceed with the calculations. In order to do calculations, as I said, I need to express my new variables, old variables in terms of new variables. So which can be easily done. A k dagger A minus k is equal to inverse matrix, which is written here. UK, VK, VK, UK, BK dagger B minus k. So I will plug in this operator in terms of, I plug in all operators expressed in terms of new operators and request that off-diagonal term disappear. It gives me second connection between coefficients u and v. So I will have a system of two nonlinear equations, algebraic equations for u and v, which I will solve, find coefficient u and v, and find the energy of my collective excitations. Okay? Okay. Okay. So H tilde minus E node tilde is equal to sum over K psi K. So this is psi K, A dagger K, AK. A dagger K is equal to UK dk plus VK B minus K. So UK B dagger K plus VK B minus K. This is B dagger. B is of course equal UK BK plus VK B minus K dagger. Okay, so this is this term. Then I have term plus sum over K, beta K, and I have a product. AK, A minus K, AK dagger, A minus K dagger. So UK, BK dagger plus VK, B minus K times UK, B minus K dagger plus VK, BK. This is the first term. Just follow me because, of course, I stay with a piece of paper. I did this calculation at home, but I don't look at this paper because I'm doing the calculations. Plus the second term, A minus K, AK. So A minus K is VK, BK dagger plus UK B minus K times VK B minus K dagger plus UK B minus VK. Good. Let's now open brackets and collect term in front of the BK dagger, BK, BK dagger, and BK dagger, BK dagger, BK, BK. So first of all, this is sum over K. Let me write first BK dagger, BK. This is psi K, UK squared. Psi K, UK squared. From this term. From this term, this is UK, VK, and VK, UK. So plus 2 UK, VK, VK. Okay? So then, sum over K, B minus K, B minus K dagger. From this term, I get VK squared psi K plus 2 UK VK beta K. So these are two diagonal terms. Let me write now of diagonal terms plus sum over k, b k dagger by minus k dagger. So b k dagger, b minus k dagger. So here we have u k b k sine k, b k dagger minus b k dagger plus uk square plus vk square beta k. And the last term, sum over k, b minus k, bk, minus k, bk. I have vk, uk, bk, uk, vk, sine k, plus the same term, uk square plus vk square, beta k. So you see that these coefficients are the same. What remains is to re-express b minus k dagger in terms of bk dagger bk. So b minus k dagger is equal to 1 plus bk dagger minus dagger b minus k from commutation relations. Okay? So therefore, I'm collecting everything. Okay, H is equal to E H tilde, node tilde. From this one, I have term which is also constant, plus sum over k, bk square sine k, plus uk bk beta k. Twice. So this is a constant. Plus sum of k, bk dagger, bk. Of course, I can replace k to minus k. There is no harm because both energy and beta are even function of k. So what remains here is psi k uk square plus vk square plus 4 times uk dk beta k. And what remains plus sum of k uk vk sine k plus uk square plus vk square beta k multiply by bk dagger b minus k dagger plus b minus k bk. Good. You see that I'm going to request that this term should be equal to 0. And therefore, in order to get this term equal to 0, I request that this coefficient is equal to 0. It will give me the second condition and second nonlinear equation to solve. So, uk vk sine k should be equal to minus uk square plus vk square times beta k. And at the same time, you remember that uk square minus vk square is equal to 1. I remind you that I do it in a parameterization u and v. You do it at home with parameterization cosinus hyperbolicus theta k, sinus hyperbolicus theta k. Okay? I deliberately wrote this equation in this form because in order to solve it, we will take this equation number 1, square it, and as a result, we will get quadratic equation which we will solve. However, let's look at this equation. In the right-hand side, u squared, v squared, and beta k are positive. Psi k is also positive. Therefore, the product uk and vk should be negative. So uk times vk is negative. Because by squaring equation, we get some artificial spurious roots. And in order to get rid of unphysical roots, we need to remember that we take only those roots which satisfy to this condition. Okay? Okay, the rest is very straightforward. So,
hello.
yes.
Sorry, I lost where you said UK VK smaller than 0. Can you repeat a bit?
The left-hand side. You see the left-hand side. In the left-hand side, psi k is positive. In the right-hand side, uk square plus vk square is positive, beta k square is positive. So the right-hand side is negative. So the left-hand side, uk vk times positive function is equal to negative function, which means the product uk and vk is negative. Okay?
Thank you.
Good. So from this equation, uk square is equal to 1 plus vk square, and I take square of the first equation. So uk square times 1 plus uk square, sorry, vk square. This is square of this term times psi k square is equal to 1 plus 2 vk square square beta k square. Okay? So what I did, I take a square of this equation, uk square, vk square, psi k square, and I plug in uk square. And also I plug it in here. This is what I have. So vk to the fourth power psi k square minus 4 times beta k square plus vk square times psi k square minus 4 times beta k square minus beta k square is equal to 0. If I divide all equation by this product, I get vk to the 4 plus vk square minus beta k square divided by psi k square minus 4 beta k square is equal to 0. This is big quadratic equation. I can solve it expressing vk square. So vk square is equal to minus 1 plus minus square root of 1 plus 4 beta k square psi k square minus 4 beta k square divided by 2. I have 2 roots, as I said, but we will take only one, namely those with a sign plus. Why? Because we made a conjecture that vk is real function. If I take a root with a minus, I will get a contradiction to this conjecture. So vk squared is then 1/2. I have a square root of 1 plus 4 beta k squared divided by psi k squared minus 4 beta k squared minus 1. At the same time, uk squared is 1 plus vk squared. So uk squared is equal to 1/2 square root of 1 plus 4 beta k squared over psi k squared minus 4 beta k squared plus 1. Good. I obtained u and v coefficients. Now, let's look at what we have obtained. First of all,
hello.
let's denote e k squared as psi k squared minus 4 beta k squared. If we look at the definition of psi k and beta k, this is epsilon k squared plus 4 times epsilon k beta k plus 4 beta k squared minus 4 beta k squared. So this is plus 2 epsilon k beta k. Okay, just a notation. Then vk squared is equal to 1/2. We have denominator which is ek squared, and here we put it into the denominator. So this is psi k over ek minus 1. And vk, uk squared is psi k over ek plus 1. Then uk squared plus vk squared is equal to psi k over ek. Right? uk squared times vk squared is equal to 1/4 product of this, so there is 1/2, sorry. 1/4 psi k squared over ek squared minus 1. I open the bracket, so this is 1/4 beta k squared divided by ek squared times 4. So this is beta k squared divided by ek squared. But now we remember that the product uk vk should be negative. Namely, I'm writing it here that uk vk is equal to minus beta k divided by ek. Good. So now this term is 0. I just delete it. Because this is what we request. Now uk squared plus vk squared is equal to psi k. This is psi k divided by ek. This is uk vk is equal to minus 4 times beta k squared over ek. And psi squared, psi squared. So this term is then h tilde is equal to e naught tilde plus sum over k e k beta k dagger bk. Because I have psi squared minus 4 beta squared divided by ek, and by the definition, this is ek squared. So I obtained this. Now let's look at this constant. So this is vk squared, which is 1/2 psi k ek minus 1 psi k minus uk vk 2 times beta k squared over ek. Yeah. So this term, if you massage it, it's psi k squared minus psi k minus beta k squared. So I will delete it here, you will rewrite it. So this is 1/2 ek minus psi k. Okay? This is a constant. I'm coming back to discussion of this constant maybe next week, maybe when we discuss superconductivity. I'm not going to spend time for discussion of this constant, although it has some transparent form. So this is our result. We diagonalized the Hamiltonian and we found the spectrum, namely epsilon k. And let's look at this spectrum. So epsilon k is square root. I'm plugging in here. So epsilon k, we consider three bosons. This is h squared, k squared over 2m. So first of all, we have term h squared, k squared over 2m squared. This is this term epsilon k squared. But we also have term 2 times beta k. So this will be therefore u k over v times n. And times h squared. You didn't correct me. This is 4. Because I take square of this, epsilon k squared plus 4 times epsilon k bk. So therefore, I have h squared k squared over m. That's it. This is my spectrum. Let's look at it. I will draw it, but you already realize that this is the same spectrum which I derived using Bogoliubov transformation. I will also use that u is equal to 4 pi L squared h squared over m. And I use the fact that P is equal to h k. Okay, so now I'm rewriting this spectrum. So the spectrum epsilon k is equal to square root over c squared p squared plus p squared over 2m, where the sound velocity c is equal to h over ml, and here we have a square root over 4 pi n l cubed. And you immediately realize, so n small is n over v. We have the same gas parameter which I began with. Indeed, we took into account effect of interaction, and we found that it results in sound-like excitations. However, the sound velocity is proportional to square root of the gas parameter. So if we plot this spectrum for small k, for small p, it goes linearly, and for large p, it goes quadratically. So epsilon p is equal to Cp if second term is smaller than the first one. Namely, p is smaller than 2mc. And it's equal to p squared over 2m if momentum is larger than 2mc. So this spectrum, which describes us sound. On last lecture, I used the representation of the modulus and phase, and I showed you that fluctuations of density satisfying the wave equation. So we do have sound. These are phonons. And these phonons are described low line excitations for in the long wave limit. For the short wave limit, we come back to free particles p squared over 2m. So this is so-called Goldstone mode. So linear, the gapless branch of excitation is called in the literature Goldstone mode, because let's look what happened here. We have a Hamiltonian which satisfies the gauge invariancy in such a way that we can add, multiply each operator's creation and annihilation by corresponding phase, and my observables are not sensitive to this gauge transformation. The Hamiltonian actually preserves its form. However, by doing truncation of the Hamiltonian, I broke this U1 so-called gauge symmetry, because this term explicitly, it locks the phase. It contains two creation and two annihilation operator product. Therefore, as a result of breaking continuous gauge symmetry corresponding to the phase factor, I obtained the gapless branch of the excitations which are formed. This is in agreement with the Goldstone theorem, which requires, first of all, some continuous symmetry is broken. Here, continuous symmetry is attributed to the phase. For those who are experts, I am telling that this is so-called U1 symmetry. Then we have a short range interaction, and as a result, we have this Goldstone. Now, let's look at this spectrum. This is U as a function of K. I told you that in principle, from certain point, all my calculations are correct also for long range interaction. You do it as a homework. Let's plug in here Coulomb interaction, which is 4pi squared over q squared over p squared. Therefore, p squared and p squared will cancel out, and what we will get here is just plasmon frequency squared. So, for the case of a short range interaction, the spectrum is gapless. For the case of long range interaction, the spectrum is gapped, and excitations in charged bosonic system below the condensation temperature are nothing but fluctuation of a charge density, which are plasmons. We again obtain the same plasmonic mode, which we discussed when we considered electron gas subject to Coulomb interaction. Why we don't have gapless excitations? Because one of the necessary conditions of Goldstone theorem is violated. Namely, we don't have short range interaction anymore, we have a long range interaction. We will come to this point when we discuss excitations and superconductors. Superconductivity, as we will see, is related to formation of the pairs, instability of the ground state with respect to formation of the pairs. And these pairs actually are charged. We cannot treat these pairs as bosons because the size of this pair will be much larger compared to the distance. However, we can apply the same arguments that the excitations in the system with long range interaction will not be gapless. Conditions for Goldstone theorems are violated. Therefore, we will get superconducting gap, and superconductivity phenomena will be explained actually through the same argument, and by the way, through very similar technique which I used for calculation of that spectrum. The last two things which I would like to add in remaining 10 minutes is thing number one. We computed, we diagonalized Hamiltonian using this UV transformation. We can do the same computing the number of particles standing out of the condensate. I told you that for ideal Bose gas, all particles at temperature equal to 0 fall into the ground state, namely to the state with the lowest possible energy. In the box, this is 0 energy, 0 moment. However, the interactions prevent all particles be in the condensate. And therefore, even if temperature is equal to 0, due to interactions, we have some particles staying out of condensate. So this computation can be done, and I encourage you to do this calculation. I will only present results. Again, this is not mandatory problem. So calculate the number of particles in a condensate. The answer for three-dimensional gas is M node 1 minus 8 over 3 square root over ml cube divided by r. Again, we see small parameter ml cube. So this is the number of particles in the condensate at 0 temperature. Observation number 2. If we look at this spectrum, and you remember in the solid state, in the course of solids and phonons, you had a spectrum like that. So this is say pi over A. These were acoustic phonons in a lattice. And the spectrum had negative curvature. Moreover, at the boundary of brilliant zone, you had a group velocity equal to 0. Here, we have a completely different shape of spectrum. Namely, if we compute dEp over dP modulus for any p positive, we will get that this is larger than the sound velocity. So the curvature of the spectrum is positive, which means that your sound-like excitations are unstable with respect to decay on other two excitations. Unlike phonons in a crystal, where the curvature is negative, and it guarantees you that the sound-like excitations are stable. So if we take into account what I said, that the curvature is positive, we can consider the process when one excitation, now the solid line denotes this excitation, bosonic excitation, decays on two other sound waves. One can take into account this sort of processes of decay and compute the inverse lifetime of the quasi-particles. Because we defined ourselves in the first lectures that the quasi-particles here, these quasi-particles are sound waves, are well defined if the inverse lifetime is much smaller compared to the energy of the quasi-particles. In the long wave limit, the energy of the quasi-particles is proportional to the moment. If you compute 1 over tau, which is gamma, which depends on the moment of t, you will get that this for 0 temperature is proportional to the momentum to the 5th power. Three-dimensional, neutral, weakly interacting Bose gas. And this is temperature equal to 0 result. So, even at 0 temperature, as I said, these quasi-particles possess finite lifetime. However, this lifetime is proportional to much higher power as the power of the spectrum, which is linear in T. And therefore, the quasi-particles are well defined. These calculations, this lifetime of phonons in weakly interacting Bose gas is called Belyaev damping. Belyaev. There are different spelling. I'm not sure that this one is better than another one. So this is Belyaev damping. For enthusiasts, I explain you how to write it down. You can look in the literature for all calculations and compute this Belyaev damping for the case of three-dimensional electron gas. Bose gas, sorry. Now, if we are at finite temperature, then we have additional mechanism of scattering. So the sound wave can scatter on density fluctuations. You see here it's decay 1 and 2. Here it's scattering on the density fluctuations. This mechanism is valid only at finite temperature. At 0 temperature, it doesn't exist. This is called Lambda damping. Very similarly to the Lambda damping which we discussed in the plasma, namely when we considered electron gas subject to the Coulomb interaction, and we got plasmons as the excitations. I'm not going to derive neither Bielayev nor Lambda damping, but the message is that the quasi-particles are well defined even at final temperature, provided the temperature is not sufficiently high. But I encourage you to look at the literature. This is interesting, and to learn what is Lambda and what is Bielayev damping. And moreover, I told you that this method, which I applied to study many problem, is complementary to the method based on solution of Gross-Dostoevsky equation. However, it gives access to not only spectrum of elementary excitations, but also inverse lifetime of these excitations. Okay? Good. I finished. If you have questions, it's time to ask these questions. By the way, for those who would like to proceed with the calculations, can equally consider charge depositors and analyze Bielayev and Lambda damping for three-dimensional charge deposits. Good.
Professor? Hello?
Yes.
Sorry, so I was looking at the Hamiltonian, so you inserted a commutator for the minus k term, right? If I'm not wrong. But then I didn't see the minus k anymore.
Look, I have a summation over two. And my coefficients, namely psi k, beta k, are even function of k. Therefore, under summation, I can make a change of variable k to minus k. And everywhere where I have a bk, b minus k dagger, I can equally write bk, bk dagger, because the coefficient in front of it is even function of k. Therefore, I don't care whether it's written k or minus k. I only care about k and minus k indexes in the anomalous form, namely ak dagger, and ak. Because you see that the momentum is conserved, k minus k, minus kk. Here, it's a kk momentum which is conserved. It's of course also conserved, because you create one particle, you annihilate one particle. If you create two particles, you create one with k, one with minus k. I have momentum conservation in all terms, but this function and this function is even function of k. By construction, you see that these are even function.
Thank you.
Look, this is important. I deliberately spent 2.5 lectures for discussion of Bogoliubov spectrum, deriving it basically with 3 different methods. Because, first of all, it's deep physics, and really deep and important physics, which actually goes beyond condensed matter physics. This Goldstone theorem, by the way, was introduced in high-energy physics. And moreover, methodologically, I presented 2 completely different methods. One is based on solution of nonlinear equation. And if you look in the modern literature, many people are dealing with Gross-Dostoevsky equation because it has very broad domain of applicability. So in many cases, of course, analytic solution is not possible. And people study this Gross-Dostoevsky equation on a computer. However, due to nonlinearity, there are interesting phenomena encoded in this physics described by nonlinear Schrödinger equation. In particular, this nonlinear equation can lead to existence of solitons. This is one and first and obvious implementation of nonlinearity. In principle, it's very interesting to study solitons as well. I don't have time. We are dealing with some basic knowledge, and I don't have time to be more specific and give you lectures about solitons as a solution of nonlinear Schrödinger equation. But this is very interesting direction by itself. And as I said, this Gross-Dostoevsky equation is equally applicable for propagation of light in fiber optics, where the same type of nonlinearities appear. On the other hand, today we discussed this diagonalization of the Hamiltonian, And this is ideologically one of the main tools of the modern condensed matter physics. So in order to get the lowest lying excitations and define low lying excitations in the physics, one needs to actually do something with the Hamiltonian in order to bring it to the diagonal form. It either analytically or numerically, when we are dealing with a huge matrix, and you need to diagonalize it using Lanczos algorithm or whatever. And this is why, by the way, that in the solid state physics, the matrix of the Hamiltonian is huge, is sometimes 2 to the power n of the particles. So in the reality, 2 to the power 10, it's already 1000, almost 1000. 2 to the power 30, it will be 10 to the power 9, and so on and so forth. So even modern computers are very much limited in finding exact diagonalization. As I said, 30 particles, it's already a matrix 10 to the power 9 by 10 to the power 9. This is why the exact diagonalization can be only done for relatively small clusters. Although with modern technology, this size of cluster of course increases. There are some different methods, density matrix renormalization group, numerical renormalization group, Monte Carlo, which are very powerful for solving many value problems. And I hope you will learn some of these techniques during your numerical 2 course, which is going to be in this semester. However, literally all what we are doing, most of what we are doing is related to diagonalization of the Hamiltonians. Okay.
Sorry, Professor.
Yes, please.
You used the commutator of BK dagger equal to 1. Is it a condition that you wanted to use, or it is from the definition of operator?
I said generally BK prime dagger minus BK prime dagger BK is equal to canonical symbol delta K prime K. In the term, what I requested, I put K equal to K prime because in this case we have 1. If K is not equal to K prime, you can immediately see that this new operators BK will satisfy it automatically. So the dangerous point is when the 2 momentums coincide. And it gives me condition for the determinant. The determinant of my matrix is equal to 1, or UK square minus VK square is equal to 1, which defines me a hyperbola. Okay? We will see that for fermions, the same condition will lead to the condition UK square plus VK square is equal to 1. So instead of a family of hyperbolas, I will have a family of circles, and therefore my fermions will leave, well, the transformation, which will be equivalent transformation for fermion system, will be defined on a sphere, and sphere is compact. Hyperboloid is not compact. Okay, more questions? So next Friday, you will have a tutorial. So my plans for remaining 2 lectures about bosons are as follows. We will discuss superfluidity and vortices on Monday. This will be done with a blackboard. On Wednesday, I will spend all lecture with the slides because I show you, first of all, the experiments in ultra-cold gases, this time of flight experiments. So how this phenomena of Bose-Einstein condensation was discovered experimentally. Then I show you how this equipment works, namely what is the system of cooling, how to cool down this system, because this phenomenon, as you can see, occurs at very low temperatures. And what is the meaning of temperature? So some basic mechanism of cooling, evaporating cooling, so-called Kiselev cooling, cooling based on the Doppler effect. And then I discuss optical lattices, so actually experiments with the cold gas on optical lattices. And maybe we have time to discuss Feshbach resonance. This is the mechanism to fine-tune the interaction. in the system. But as I said, I will do it with the slides because I'm not able to draw experimental devices on the blackboard. And then Monday, Wednesday, I told you, these are 2 lectures. On Friday, there will be tutorial. And then we finish half of the course. And I start the second half with 1 or 2 introductory lectures to the theory of phase transitions. And then we proceed with the superconductivity and magnetism. Okay. That's all for today.
Oh, before you go, sir, you gave some instructions at the beginning of the class. Sorry, I came a little late. Can you repeat some of the instructions?
Which instructions? I don't understand. Which instructions?
I heard you saying something about
well, I said
homework.
That homework. I sent today a 1-page file containing 12 non-mandatory problems which I suggest to solve for the training and for repetition in some different contexts, what has been done in the previous 8 lectures. I sent it only to ICTP students because I don't know if for students would also like to receive this problem or not. These are problems which I just suggested for fun, so to say, or for improving your computational skills. These are not mandatory, and I'm not going to be back to these problems and discuss them. However, the homework which I'm going to distribute either at the end of next week or on February 15th, as I said, in the middle of February, this is going to be mandatory. I will send it to everybody. This homework will contain some problems for all 4 chapters, namely fermions, bosons, superconductivity, and magnetism, and you will immediately be able to start solving first half of the homework. This homework is mandatory. I will collect it, check it, and discuss all problems in one of the last meetings of my course. But since several people asked me to tech and to type this non-mandatory problem, I promised it and I did it and sent it to some of you today. But repeating, these problems are for you, not for me. Therefore, please don't approach me with a question how to solve this problem. I already explained how to solve this problem, and please don't approach me showing that with the questions I don't know how to start. If you don't know how to start, you go to the lectures, to textbooks, and then you see if you are able to solve it or not able to solve it. These problems are just facultative. This was maybe instructions which I gave it to you. Okay, please, I only see this chat on the screen. Those from Rwanda who would like to get these files, please send me emails today. And I will respond to this email and send you the PDF file.
Okay, Prof, I will send you our mail list so that you can forward it there.
Would be great if you send me mail list and again with names. So sort of a very short file saying first name, last name, email. First name, last name, email. That's it.
Okay, thank you.
Anything else? By the way, how with this blackboard which is now tilted? Can you see?
It was
clear.
good for me.
Very clear today. I love it.
And
Yeah, me too.
Because microphone is now much closer. Is it better sound or not?
Better.
Good, good. Then this next COVID team meeting will be on Thursday, and maybe some decision of how we proceed will be taken, namely we proceed with these online lectures or we will be allowed to have in-person lectures. Because you know, Friuli now is in yellow zone. In principle, in Trieste, both in university and CISA, they resume in-person lectures. So maybe we will have chance to do the same here. Let's see. I cannot promise anything, but I will keep you informed immediately if any important decision will be taken. Okay. Thank you. Till Monday.